Akshay and I have actually known each other for a really long time. I remember that I think we first met at Justine Sherry's house in Berkeley when Akshay was an undergrad at UC Berkeley. I was still a grad student in the UK, and we were hanging out there watching the UK election, of all things.
This is the one where David Cameron got elected, right?
This is the one where David Cameron got re-elected prior to him burning the house down with Brexit. So, good memories all around. Good memories all around. Actually, has since then moved on to MIT, where we actually spent a couple of years in the same place, and has been doing some really fun stuff with networking, broadly defined, but a lot of congestion control, a lot of things up and down the network stack that I've always really enjoyed because it's really outside the box thinking and the kinds of papers that I love reading. So it's a great pleasure to have him here today for our first in-person sysread of the semester. And I'll hand it over to Akshay to tell you about Bertha. And then at the end of the talk, we'll have time for questions. Akshay is also here for the rest of the day. So if you like what you're hearing and you want to catch up with him, then feel free to grab a time afterwards, and you can ask more questions. All right.
Sorry to interrupt. Am I the only one who's not getting a separate window with the display as well? Is everyone else getting the display on its own?
Oh, you probably want to screen share. Yes. It's my bad for
no problem.
Good catch, Shriyam. So can you join the Zoom so that you can screen share your display? All right, thanks, Shriyam. Now, actually, over to
I would also recommend that Akshay maybe mute his laptop to.
He hasn't joined audio.
I think it's muted.
Okay, all right, we're good. Let's go then. Thanks.
Things are sort of okay. We're good. All right. So as Malta said, this is going to be a talk about Bertha, which is joint work with Panda from NYU, my advisors, Hari and Mohammed from MIT, Arvind from UW, and Scott from Berkeley. So many professors. So I'd like to start with a very straightforward question, which is how should we write applications that use the network? And as we can all imagine, especially in the current times, this is a very important class of applications. So I think it's important that we sort of understand and sort of optimize the way that we write them. Okay, so the answer, if you ask Beej from Beej's Guide to Network Programming, which, by the way, this website has gotten way more slick since the first time I saw it. Like when I first saw it, it was this like beige, like Web 0.9 sort of HTML sort of website, and now it is very fancy. But the answer, if you ask him, is to use the socket API, which is the API that the kernel's networking stack exposes. So there are a set of syscalls. Your application can call the syscalls, and you can use the network. So we're all happy. So let's try to understand what this API is doing. So from the bottom up, we have our network infrastructure, and this is the system that actually transmits our packets. And on the top, we have our application. And in the middle, we have our network stack. And the network stack's job is to expose an API that the application can use, as we just discussed, that sort of connects these two things together. So both the network and the network stack have traditionally been this sort of well-defined and standard set of functionality. And they've sort of provided this for a very long time. And this is sort of our standard layering model with its narrow waist, et cetera. And this functionality has been general enough to support a pretty wide range of applications. So because the network API has been this general and relatively static part of the picture, changes to it have been relatively hard. So historically, it's been the application layer where that was the place where all the dynamism and diversity of functionality in our applications was happening. And the application layer is so central to evolving our use of the network that around 10 years ago, Jan Stojka from Berkeley was writing papers arguing that HTTP is going to become the new narrow waist of the internet, and all of the dynamism and diversity is going to happen on top of HTTP. And to some extent, we've actually seen this play out. So like with the rise of RPCs and like HTTP evolving into HTTP2 and now QUIC, which is going to become HTTP3, we've sort of seen more and more common features being incorporated into this application networking layer. So as we know, the network hasn't been standing still this whole time. So like with the rise of SDN and cloud computing and the increased use of offloads to deal with the end of Moore's law, we've sort of seen all of these trends that sort of converge on the functionality that the network has been offering has been increasing over time, and especially recently. and even like work from this group. So like Theo gave a talk at MIT a while ago, proposing the system P4 Visor, where you like the network can offer like more protocols, more features, even more easily. And the sort of end conclusion of this is that the network really isn't about just packet delivery anymore, and it hasn't been for a while. So like parts of our application logic are moving into the network. So we can remember from sort of 2 slides ago that the application layer was historically the place where people have been able to change things. And as the network started acquiring these new features, the sort of natural way for application developers to adapt to this was to use what I'm going to call the communication library approach. These communication libraries basically bridge the gap between the features that the network is providing and the application's code. So some examples would be using the AWS SDK to access a managed publish-subscribe messaging queue, or to do sharding or load balancing in the cloud, or to use the gRPC API, which then might have its processing offloaded to hardware, or to use libID verbs to access an RDMA device. And in that case, we're actually just bypassing the traditional network stack altogether. So that's sort of how things have changed infrastructurally, but what are the architectural implications of these changes? So one observation is that our sort of venerable networking stack in the middle here is being papered over or replaced entirely by these communication libraries, because modern applications are demanding more from the network, and the network stack is just offering the same fixed set of functionality that it's been offering the whole time. So along our current trajectory, we can sort of expect that the use of these communication libraries is going to increase over time, and they're going to become even more essential to the operation of our applications. So I'm not necessarily saying that these communication libraries are bad. I think it's a good thing that applications are able to express the functionality that they actually want, rather than being forced to rely on some one-size-fits-all bare bones API. But I do think that there are 2 things that the communication library approach is sort of missing, and that's composability and portability. So by composability, I mean the ability to combine the functionality of 2 or more potentially unrelated libraries together into a single application's use of the network. And by portability, I mean that that application should be able to run correctly in multiple different network environments, no matter what the set of network features that that network environment is offering.
Akshay, can I ask a quick question, please?
Yeah, of course.
Yeah, so when you say there's a lack of composability, is it because essentially what you're doing is you are saying you're not getting like a little feature add-on to an existing network stack? You're essentially replacing your network stack with some other network stack. So this feature requires network stack 1, and this one requires network stack 2, and you kind of have to choose between them. And if you try to use both of them, they may not work together. Is that what's going on?
Yeah, exactly. I'm actually just about to go into an example.
Okay, all right, great, thank you. I'll shut up, thanks.
Okay, so Sriram's question is a very good question. So in this example scenario, what we want to do is compose OpenSSL, which is a library that implements TLS and gives us TLS connections, with an RPC library. And this is a pretty common use case. Many applications want to do this. So we start with the current socket-based networking stack, which is represented by this gray rectangle. And the API for our socket-based networking stack, as remember Beej's Guide to Network Programming told us, is to use the POSIX API calls of read and write, or if you want, like send and receive. Okay, so now what happens if we want to use this socket with the OpenSSL library? So OpenSSL is providing us a nice function for us to do this. It's called SSL set file descriptor. So we call this function with our file descriptor, and we get a new connection back, which is an OpenSSL connection. And this connection's API is slightly different. So now you have to call SSL read and SSL write in order to use the connection. And if you were to call this original read write POSIX API, the state of your OpenSSL connection might get messed up, because you're writing random bytes into the string. So far, this is sort of okay. Like the API has changed, but we can sort of deal with that in our application by changing our application to sort of use OpenSSL. But now what happens if we try to compose this with our RPC library? So we sort of run into a problem. There's no way to communicate to this RPC library that this connection that we're passing it is actually this OpenSSL connection rather than an original socket connection. And that calling read and write from this RPC library would be unsafe on this object that we've given it.
So you're assuming here, actually, if I could just ask for clarification, you're assuming here that the connection gets established outside the RPC library and then handed to the RPC library,
yes,
right?
exactly.
Another way would be to ask the RPC library to make.
Exactly. So like as Malta said, the way that people handle this in practice is that you ask your RPC library to create a connection for you, and the RPC library has some set of backend TLS implementations that it supports. So you ask it, okay, I want gRPC, for example, to establish an open SSL connection, and then gRPC goes and handles the establishment of this connection, and then it knows that it's an open SSL connection because it's the thing that made the connection, and it can like make the correct calls accordingly.
So I'm sorry, like every systems talk needs to have a PL person coming up and showing, acting like an ass. And so this is my moment to shine. But this is like a subtyping problem, right? Like you got a subtyping issue and you're saying, I want to have a refinement of sockets and not, and I want to be able to override the previous sockets and so on. And we kind of know how to solve these problems linguistically. Is this a linguistic phenomenon that I'm looking at and you're stuck in C land and your life sucks and maybe you use Rust and traits or something, we'd be better off? Like what's going on here?
We're looking for Rust and traits. I would ask you to wait for 5 minutes because Rust and traits are going to show up.
In Golang, you open a socket in HTTPS with HTTPS library, and then use that for the gRPC.
Right. Yeah. So that's kind of similar to what's happening here, right? Like so in Golang, you might have like when you open a socket, you don't call like net.dial and then have an object and then pass that into the HTTPS, right? Like you sort of have the HTTPS library and then you ask that to give you connections as they become available.
Yeah, because the HTTPS library is built to simplify it, so you don't need to call the.
Right. Yeah. So like it is I would say optimized for that use case, but let's say you wanted to do some other kind of composition, right? The only composition that the HTTPS library in Go is supporting is that one composition. And if you wanted to do something else, you're sort of like, out of luck.
Right. I think this also goes to Shriram's question that I feel this is not just a linguistic problem, right? I have written a lot of software where I wanted to manage the sockets and the connections for some reason or another, right? And then I still want to use these libraries, but these libraries right now tell me we are going to manage the connection for you. We are going to have our receive loops. We are going to have threading, and then like everything ends up in the RPC library. That's a systems problem, not just a linguistic.
And for example, they also hide the TCP options.
Yeah, you're sort of entirely dependent on the RPC library developer to give you the sort of support for things that you want. So like if you go and look at the gRPC repository, there are like GitHub issues saying like, I want to use systemd to manage my connections because that's like a really like nice thing for my deployment. And the gRPC developers are saying like, sorry, we're just not like, that doesn't like that use case doesn't really matter to us. So like, you're sort of out of luck and like, please go use some other RPC library.
I don't entirely agree with Malte. I mean, this is a matter of like layering on how your constructors are, but I get your point. I don't entirely agree with it. But, yeah. Okay. But don't let us interrupt you. Sorry.
Yeah. So let's talk about portability next before we get into our like fun Rust stuff. So not all networks are the same, and communication libraries have, as a result, for optimization and performance reasons, developed sort of specialized implementations for applications to use to run in those specialized environments. So continuing with our TLS example, there's at least 5 implementations that I could think of when I was writing this slide that you could use and choose between depending on what your network environment is. So you could use like AES native instructions if you have a modern CPU, or you might even end up disabling TLS entirely because your container's runtime environment already supports another implementation of encryption and authentication. So running it again in the application is sort of wasteful in that case. And this information, if you know, can't even be known at compile time all the time. So like what your network environment is and like what your container runtime environment is, like you don't necessarily know that when you're compiling your application. And basically what this means is that today, you can either give up on specialization and use the sort of lowest common denominator socket APIs to build your application. So you give up on performance in order to get portability. But of course, no one wants to do that. What everyone does is instead we build applications that are highly specialized to their runtime environments. Like you build your application assuming that AWS Cloud HSM is going to handle encryption for you in hardware, and you give up on portability instead. Okay, so how can we think about addressing these shortcomings? So for our composability problem, what we want is something like what Shyam said, like you want a nice interface and traits and some standard composable interface that you can use to like sort of compose sockets together and compose libraries together. And one way to think about this is, of course, like Rust traits and Go interfaces. And we ideally would want communication libraries to use these sort of language features to compose nicely together. But even this is sort of only limited to compile time. So ideally, what we would want is even after compile time, when we're actually going and talking to someone else at runtime, we want to make sure that the person we're talking to has a compatible composition of libraries as us, so that we are sort of more sure that the connection will actually work out. And on the portability side, of course, what I'm arguing that we should have is sort of late binding of our feature implementations to correspond and fit to like whatever the network environment supports for us.
Like user-land network stuff. Like user-land network stuff.
Yeah, exactly. So like everything that I'm talking about today is going to be sort of like a user-land network stack. One sec, let me just disable notifications on my phone. It's really annoying. Okay, so our answer to these two challenges is a what I'm going to call an extensible and runtime reconfigurable networking stack that we call Bertha. So we make it extensible by allowing authors of communication libraries to plug in their library's functionality into the network stack instead of having to arbitrarily wrap other libraries, as we were just talking about. And what we mean by runtime reconfigurable is that the network stack is going to decide at runtime, specifically in our case, when it's establishing the connections, what implementation of each network feature that the application wants that it's actually going to use for that connection. So Bertha is just like any other networking stack, except it's in user land, of course, in that its core functionality is to provide applications to connect to other endpoints over the network. The key difference is that in Bertha, applications can request that their connections have some additional features, and Bertha will then go and try to provide those features using whatever implementations are available. So this is a good point for questions before I continue. Like, I think we've had a good discussion so far.
I like this idea of a wide communication-based composability, but this is more application-centric. I feel like if I were a large hyperscaler, I would also want some unique policies that are not by communication or they're not by targets. Basically, like Facebook would have some network policies that they add into their network stack, and you would want maybe the application to negotiate that with the kernel versus negotiating with the client. You also support that level of composability.
So that's a good point. What kind of, do you have an example of this?
Yeah, so like firewalls, weight limiters, I think that you're implementing ePPF right now.
Yeah.
I suspect you can implement those in your user space stack as your
Right. So I think that kind of thing is expressible with what we have, but I think the focus of this work is more on like doing it across the network and making sure that both sides have the same thing. Okay, so if there are no other questions, what about Zoom people? Do Zoom people have questions?
Any questions on Zoom?
I think we're good.
Okay, cool. All right, so to explain what I'm talking about here, I'm going to first discuss what our structure of Bertha's composable and extensible approach to building a networking stack is, and then we can sort of get into how this structure enables the late binding that we want, and then I'll end with some optimizations that the structure enables. All right, so Bertha's core abstraction is what we call a tunnel, which is like a tunnel, but better. So the tunnel abstraction is how applications can specify which network features they want to use. So that's how applications interact with tunnels. And then on the other side, library developers are going to provide libraries that implement network features that the application can then plug into. Okay, so note that while I've sort of logically separated out these roles, in practice, they could, of course, be performed by the same person. So for example, I am the world's only Bertha developer right now. So I'm writing both Bertha applications and Bertha tunnels. And then like future Bertha application developers could do the same thing. They could sort of split out their application's functionality into their application, like sort of business logic, if you want to call it that, and then whatever their sort of network processing is.
I don't fully understand what an arrow is in that picture. How do I read an arrow?
I would say it's an interaction, I guess. So
Applications interact with channels through usage, and channels interact with people through feature.
So library developers provide feature implementations.
Okay, I was trying to understand the bidirectionality of that arrow. Maybe I shouldn't be reading the arrow.
So, yeah, I think maybe to the same point, is it feature property of a channel? Are you going to have like different channels for different features?
Yeah, exactly. Okay. Yeah. Okay, so let's sort of get into how channels work. So we're going to start with the simplest possible building block in Bertha, which is a base connection with no fancy features, like provided by an existing networking stack, for example. So the application is going to call send and receive, which is our Bertha connection API on the base connection. And in this case, all it's going to do is like shim socket API calls. So nothing fancy is happening. Okay, so now let's bring a channel into the picture. This is going to be a serialized channel. So channels work by taking in a connection as input and returning a new connection with some added features as output. So like exactly what Sriram was suggesting earlier. They're basically like a connection transformer. So you take in a base connection, you transform it into a serialized connection. The serialized connection encapsulates the base connection that you pass to it. Okay, so if we use this serialization channel, when the application sends and receives messages, the serialized channel is responsible for doing whatever features that it's providing. So in this case, it's going to serialize and deserialize messages, and then pass those down into the base connection, which is then going to use whatever means. So for example, with the socket kernel networking stack, it's going to use sockets and the kernel networking stack in order to actually carry out the underlying transmission. Okay, so let's look at how we solve our composability problem using an example microservice application. So this application that I'm going to talk about has three requirements. It wants connections between microservice instances to be serialized. So it wants a convenient application object interface. I think we sort of all understand what serialization is. It also wants encryption for authentication and privacy. And then it also wants a fast path. So what I mean by fast path is that if the endpoint that we're connecting to is on the same machine, then we don't want to go through like virtual networking and the usual socket like UDP or TCP networking stack. We want to use something faster like Unix domain sockets. Okay, so what does this look like in Bertha? Of course, Bertha is written in Rust, so this is Rust syntax. I hope you're not intimidated. Some people are, but I think it's getting better over time. So the application developer is going to instantiate tunnels representing these three features. So we instantiate a serialization channel, the TLS channel, and a maybe local channel. And these are all channels that are provided by libraries that the application developer is going to link with. And the application developer can find these in the way that we find libraries like going
May I quickly interrupt? I had a quick question. Hi, the question I had is, does the order of these channels matter? In other words, are you first creating a TLS channel and then wrapping it in a serializable channel, and then a maybe local channel, or?
That's a fantastic question. I think we're going to get back to that in about 3 minutes. Oh,
yeah, I think when you step on that cable, sometimes it does funny things. So we could just maybe unplug and yeah, there we go. There we go. We're good. We're good.
Better?
Thanks.
Okay, and then the way you compose these things together is using this make stack macro. And this make stack macro is not complicated. If you're familiar with lists, it's basically making a const. It's not fancy. And then we have this connect function, which Bertha is providing, and I'll get into how connect works later.
So I find it a little curious that you expressed the composition on line 4, and none of the previous things expressed any composition. Is that by an intentional design decision?
Yep.
Okay.
So we don't want each of these things to have to think about what they're composing with. So
well, you kind of do, right? Because on your previous slide, you said they're going to take like a connection and return a connection. So they are
so they have some
about
like type constraints.
They
have like we have a trait called channel, and channel has some like input constraints that each of
I guess, okay. I mean, I was going to ask you an ordering question because traits have like ordering issues, and that's one of the downsides of traits.
We lean heavily on the Rust like type system in order to make sure that this stack is actually going to make sense.
Okay.
Okay, so channel implementations have two components, and we're going to look at what they look like for the maybe local channel that I talked about just now. So the first component is the thing that I just talked about, the connection transformer functionality, which is over here. And all it's doing is providing a function that takes a connection as input, this R thing, and it returns a new connection that represents the channel's output connection as its output. So in our case, our function is going to check whether the address that we're connecting to is a local address. And if it is, we're going to make a local connection and return it. And otherwise, we're going to take the inner connection, which is globally scoped, and use that as our remote connection. And we're using this maybe local data path type, which is an enum, to basically unify the two cases into a single return type.
I would have expected the connection to have two parameters indicating the two endpoints, and I would have asked whether the other endpoint is in the same space as the current endpoint. That's not the code I was expecting to see.
Yeah. So
I mean,
can
self,
sort of
I'm
say
always
that,
sort of
like,
local to
this,
myself.
this adder thing is like a configuration that you pass into the channel.
Okay.
So
Oh, okay. Oh, all right. Okay.
yeah, it is like it's
Okay, fine,
effectively
fine,
the
fine,
same
fine.
thing, but like slightly.
Fine.
Yeah.
So question about the connect part. So what assumptions does that make about the connection that self.local.connect returns here, particularly about its type, right? Is this like a plain socket connection?
Yeah.
What about if I wanted to be SSL?
At least a plain, it's at least a plain socket connection.
Yeah,
Right,
exactly.
right.
It's at least a plain socket connection. It could have other features, but we don't really care. Like,
Right, but you don't know at the point when you make the channel, right? What
so
other features?
at this point, it doesn't really matter. So like
Okay.
in the future, if Rust gets like specialization or whatever, then you could imagine saying like, if this R is actually an SSL R, then I want to have like one implementation. And if it's not an SSL R, then I want to have some other implementation. But currently, of course, Rust doesn't have specialization, so I didn't implement this.
Could you solve that issue by putting the SSL connection above the maybe local channel?
Yes, totally. We're going to get to that like very soon. Okay, so the second component is going to help with our other problem of portability. So basically, remember that libraries like OpenSSL could have multiple implementations of the same like sort of channel or feature that are optimized for different network environments. So the idea of this second component is to provide some sort of abstract representation of a channel's features. So if two channel implementations return the same features, then Bertha sort of concludes that they're compatible with each other. And to actually choose between multiple connections, multiple implementations, the developer uses what we call a select, which is this thing. And in this case, I'm showing two examples of this maybe local channel. So one that uses a Unix pipe and another one that uses shared memory for communication. This select macro, just like the make stack macro, the select macro is not complicated. All it's doing is creating a struct that represents these two options.
Okay.
And then Bertha will choose between those.
So it's delegating it to runtime.
Exactly. It delegates everything to runtime. Okay.
But semantically, I should think of this as a non-deterministic choice. And so
Yes.
the two things had better be interchangeable.
Yes, the two things have to be interchangeable. Exactly.
Along what dimension though? Because a Unix pipe and shared memory are not interchangeable along all dimensions.
They're interchangeable.
On the maybe local impulse dimension.
Yeah, exactly. This
Right.
That's the interface that determines what has to be common.
exactly. Okay, so various people have been asking the same question, and I'm finally going to get to it now. So what we've described so far, it seems like we have enough to achieve both composability by layering channels together with this make stack macro, and also portability by using selects between multiple implementations and then selecting between them at runtime. And I know I haven't explained how to do that, but I promise I'll get to it later. But there's a problem with just the API that I've described so far. So ideally, we want these like very fine-grained channels, like the application developer has split their thing into very like fine individual pieces and layered them together into this nice stack. And the application developer has then like composed this stack in a very intuitive way. Unfortunately, this approach is not going to end up being great for performance, as various people have pointed out here. So let's look at our stack again. So what's going to happen here is that because we use this order, which is, by the way, it's a very natural order. So like first you serialize, which is sort of application traditional functionality. Then you do TLS, which is sort of very traditional transport functionality. And then you do maybe local, which, as I've described it, is like a routing type of functionality. What happens is that when you pass from serialization into TLS into maybe local, no matter whether the connection is local or not, you're going to always encrypt your bytes. And if your endpoint is on the same machine, you might not want to do that because maybe things on the same machine are in your TCP anyway. So if we try to stay within the scope of the story I told you so far, then there are basically two possible ways to fix this. So the first, and they both involve asking the application developer to do things. So the first is to say, application developer, please reorder these two things. And if you reorder these two things, then serialization will happen, and then we'll decide whether to our routing, and then only if it's remote will we pass things into TLS. The other way is to fuse these two things together into a mega channel, like a TLS with maybe local channel, and the application developer would somehow write this thing and then create this thing, and this thing's behavior is basically the fused combination of the two channels that I've already described. So if it's remote, it creates a TLS connection, and if it's local, then it doesn't, and it uses the passpath. So Bertha's solution to this problem is, instead of having application developers try to reason about different channel combinations or whether they should try to fuse them together, Bertha sort of outsources this to domain experts. And we define an API, which we call stack passes. And these stack passes are basically analogous to rule-based optimizations in other domains like in machine learning or in data analytics. So we want domain experts to be able to specify these transformations, this big gray arrow that I'm going to fill in very soon. And we don't want them to have to reason about channel stacks one by one. We want them to be able to say sort of like, if there is a TLS channel followed by a maybe local channel in any channel stack, then we want to be able to express that without reasoning about this specific channel stack by itself. So what we do in Bertha is we define this pattern matching sort of mini DSL for these domain experts to write their stack passes in. And being able to do this is sort of a nice benefit of our channel stack structure. So there's a well-defined place with a regular structure that sort of expresses all of the things that the application cares about. And domain experts can sort of reason about this and write stack passes that optimize it in some way. So in our example here, the domain expert is doing exactly what I said before. So it's taking, the domain expert has said, if we see a TLS channel followed by maybe local channel, then we're going to replace it with a fused version of the channel. And the domain expert is in a much better place, in my opinion, to write this sort of fused implementation of the channel than asking the application developer to do that instead.
And you get the IDE to do the coloring as well, that would be even cooler.
Oh, yeah. Like, I had to make the gradient thing by myself.
But the domain expert doesn't need to know anything about the application, right? This only has to be written once for Bertha and all applications.
Yeah, exactly. So the domain expert has defined this trait. This trait, basically the way this works is that this macro will implement this trait for various different channel stacks that have this pattern. And then the application developer can use this library and call this trait function on their channel stack, and then the correct transformation will happen.
So three questions. One is, why do you introduce this new sort of, it looks like an existential type there. Why do you introduce opt?
Oh, yeah. So sorry, opt is the new channel stack. So we have self, which is the current channel stack. Yeah. And then we return self.opt, which has a different type because the type has both TLS channel and maybe local channel. And then the output type is going to have fused TLS, maybe local channel. So it's a different type.
Okay, I don't quite get that, but let me move on. So you said you got this macro. So is the macro literally just glomming code together?
Yep.
Okay, so how does it know where to perform that optimization? You've said if there is one, you want to create this fuse thing, but you haven't said what the fuseness is, in what way it's an optimization.
Sorry,
Sorry, like if I've got the code for TLS channel,
yep.
I got the code for maybe local channel, and if I just naively compose those two, I'm going to do the same thing I was going to do before.
The implementation of this type of this fused TLS maybe local channel is not automatic. So
got it. Okay, thanks.
Yeah. Thanks. It's the domain expert's job to sort of
got it. So this is just a mechanism for declaring that this thing exists in a principled way.
Yep. Exactly.
So what's the macro doing then?
All the macro is doing is generating implementation of this function for different channel stacks with different like generic parameters. So you could have a channel stack with not just serialized followed by TLS channel followed by maybe local channel, but like all kinds of random like stuff up here.
I see.
And then you want to.
Is that why the star parameter?
Yeah, that's what the star parameter is saying. I see.
Wouldn't it be sufficient if in this case you just specified that it should reorder the channel? And could you express that? Could you say
you can totally, you can sort of say, look, this.
It wouldn't be sufficient
because I use this example.
I don't think it would suffice because the code would still do the same thing it was going to do. something still needs to make a decision saying, because I'm local, I don't need to do TLS. That wouldn't come for free.
Well, but if you nest the TLS under the local connection, then the short circuiting will circumvent the TLS.
Yeah.
Because you have now a different connection that you've created by hand.
Assuming everything was set up right, yeah, okay.
Yeah, exactly. You would have to set everything up correctly. So I did this because this is the way I implemented it, because the other way is harder and I'm lazy. So I did this instead, but like you could, of course, do the other thing.
So can we talk about the return type of this?
Yeah.
Is that the return type is a different type. It's like if use TLS, maybe local channel, right? Like if I'm an application developer, do I have to anticipate that there's going to be a fuse TLS, maybe local channel?
No, so you just say like my channel stack is some type T and I'm going to use it. And then I call like my create a connection function on it, like the connection.
Right, because this fuse
The point
TLS,
is it's
maybe
still a
local
channel.
implements
The point is it's still a channel at the end of the day.
This thing is still exactly.
Okay, that
I want to ask very quickly about the ecosystem vision for this. So 2 questions. First, how long can any one rule be? And second, can they come into conflict with other rules? For example, somebody specifies a subset of this regular expression that you got, and then somebody defines a much larger rule, which includes that subset. Which one takes precedence?
Yeah, the one that you call first. The application developer would have to, like, if whichever one they called first would take precedence. So you
Okay.
call these in. I think, you had some other question?
No, that was mostly the main thing. I was just curious about how you handle conflicts, but yeah.
And you, what was your name, sorry?
Eustace.
Eustace, okay.
The question is, you said before, like one of the motivations for doing this is because, oh, maybe I want to manage this connection by hand. Maybe I want to set certain parameters, etc. That sort of implies that you want to have configuration access to some things that are in the stack if you want to manage them by hand. What happens with Fusion in that case? Like, can you still access things that are sort of in there despite this Fusion happening rewriting the types?
So yes. So what the domain expert would, I think, do, if I'm understanding what you're saying correctly, is let's say you have some base connection here, and then instead of just maybe local channel being the end, you have some other channel that's like configuring something in the stack and like making the whatever input connection have that like configuration parameter that you want. So what would happen in the optimized case is that you would write like star, comma, TLS channel, comma, maybe local channel, comma, star. Like you can have arbitrary other stuff after this also. And then the same thing would happen here. Like whatever you put here would move to here, and then the same composition would happen.
I'm going to convect this later.
Okay, yeah. Okay, so like I need to show some graph to prove that I've actually implemented something. So with this Fusion,
You showed us types, we're done, man.
so with this TLS channel, we have some like massive cost of encryption, and then with UDP, we have some cost of virtual networking in Docker, and then with Bertha, we can skip these things because we fuse these things together. Okay, so at this point, we have a Bertha stack, which we know is sort of the right stack for our application, the one that we want to use, and we know that it's been sort of optimized because we have these stack passes. And Bertha's job now is to implement this connect function that I promised that I would come back to later, that actually provides the portability and runtime reconfigurability parts by choosing channel implementations to produce a connection for the application to actually use. And this process, the thing that connect does, we call this the negotiation protocol. So let's get into how we can do this. So remember from before that channel implementations are providing identifiers to make it possible to identify compatible implementations on either side of the network. So there are 2 ways that channel implementations can combine. So the thing that we've talked about so far are what we call exact match identifiers. So an example of this is if one side of the connection is using bin code for its serialization, then the other side better also be using bin code, otherwise they're not going to be able to understand each other. The other thing is called compositional identifiers. And this indicates that only one connection participant needs to provide the implementation of the channel, and the other side could potentially use a no-op, for example. So in the case of sharding, as long as the client and the server agree on what the shard function is and what their idea of shard function, like what the idea of sharding is, then only one side actually needs to evaluate the function on messages and forward to the correct shard. Okay, so when we want to make a connection, what do we have?
Can I just ask a question? These identifiers, are they Like, should I think of them as types? Are they dynamic values? How,
So,
how do
yeah.
I express them in that?
In the implementation, the identifiers are like GUIDs basically. So we have like specific values that the channel exports. And
Good.
okay, so where was that? Okay, we want to make a connection. So what do we have when we want to make a connection? We have a channel stack on the client side, and we have another channel stack on the server side. And from this, we can get two sets of identifiers, one from the client and one from the server. And the client, what it's going to do is send over a list of channel stack options, or like the values representing the list of channel stack options to the server. And then the server's job is to pick a stack that's compatible on both sides. So the server is going to ensure that all of the needed exact match identifiers are present in both stacks that it picks, and then at least one side has each of the compositional identifiers that are in either stack. So if there weren't any compatible stack, then the server would return an error to the client, and then the client would then complain to the developer, and it's the developer's job to go fix that. If there is a compatible stack, then the client and the server can each instantiate a connection by just like running through the stack and running the connection transformer functions to create a connection that both sides can use. And they're like sort of confident at this point that either side agrees on what the features of that connection are going to be.
And the reason the client initiates is because the client is likely to have only one stack, but the server might have many stacks.
Yeah, it's sort of arbitrary.
Okay, so there's no particularly.
Yeah, there's no particular.
Okay, the other question is, so you have these things that are sort of required and these things that I again think of as like subtypes. So is there any connection at all?
Can you explain what a subtype is? Like,
Sorry, something that's substitutable. I can take this or I can take that, which stands in for this.
Okay.
Like a channel is there are all these subtypes of channels. If the channel is sort of like a super type, and then there are all these subtypes.
Okay.
So it seemed to me that also some of these, like with the other kind of GUIDs, I forget what they're called.
Compositional.
The compositional ones might also be in some sort of relationship, right? Like I can do this or that. Would that might also be expressed in the code in some way, in some sort of type relationship or trait relationship?
Yes, I think
so. The GUIDs are really a reflection of the trait relationship, I would think.
Yeah, exactly.
Okay, so they're not actually just GUIDs sitting out in the open.
Yeah, the GUIDs represent like sort of this gets transformed or serialized, if you want to say serialized, into some like in some deterministic way into a.
So you could have generated those automatically. The type system could have generated them.
Yeah, like one implementation that I tried at first is like use the like unstable Rust like type ID function. And it turns out that like Rust developers go through a lot of hoops to make sure that you're not able to do this. So I just generated my own.
So each basically combination of features results in one unique GUID, but there are also compatibilities.
Yeah, each combination of like potential features, like things that I could support. Yeah. Okay, so one cost that this protocol sort of incurs is that in addition to any other connection establishment cost, like when I'm
sorry, I'm still processing the previous remark. I was a little thrown by that. But there's the combinations, a very, very large number of combinations. So you're generating this very. I would have thought the GUIDs were like that box over there, the gRPC bin code. One right. That box. Is there just a single GUID representing that entire box, or is that a collection of GUIDs?
It's a collection of GUIDs.
So it's not a combination. Okay.
Sorry.
Okay, yeah, I guess I misunderstood what you meant by
that. Would be scary if that was a combination. Okay.
Yeah, so like
we're good. My heart's racing normally again, so we're good.
It would also be hard if the software on the server is like exactly the same thing that's running on the client. Right?
Yeah. And you need the structure. Yeah. Exactly. Yeah. Good.
Okay.
You got to learn code.
So, okay, zero RTK negotiation. So we have a cost because the client has to talk to the server and the server has to send a response before we can do anything else, because we first have to agree on the channel stack before we can actually use the connection. So in most cases, clients are actually connecting to servers that they've already talked to in the past. So we can sort of apply an optimization that's very similar to Quick's zero RTT negotiation. And in fact, we use the same name, zero RTT negotiation, where we just remember what the server told us to use for some previous connection. And we say, okay, like this is my stack. I want to use the same thing. And then as soon as I do this, I can instantiate a connection using that stack and send some payload. And then the server, when it gets this message, can do one of two things. It can either decide like, okay, whatever you did before is still fine with me, and then it like immediately instantiate a connection and process this payload, or it can say like, no, this is not okay with me anymore. I am going to not say okay and not process the payload. I'm going to ignore the payload and instead send back a counteroffer of it's some different stack that you should use. And in that case, we're no worse off than we were in the original one RTT case. Okay, so let's take stock of where we are so far. So Bertha connection starts as a base connection, which is all the way over there, and I forgot to put it over here, and a channel stack, which specifies what the application developer wants. And then this is then changed at compile time by the stack passes into some stack that our application is actually going to use at runtime to negotiate. Then we do negotiation where we say what things we support and we actually pick one of them.
Sorry, I'm curious, what would be the GUID for the fused one? Is it each of the, would it have its own GUID or?
Yeah, so the domain, like the domain
Yeah.
expert that writes this would just make a new GUID.
Okay, or might even decide not to.
Oh, yeah.
I decide I can just pretend to be the two existing
Yeah,
ones
or
or
you can
whatever.
like.
That's left to the domain expert.
Yeah, it's not really that important.
Got it, got it.
Okay, and then after negotiation, we have some specific stack that we can use to actually make a connection, and then this connection is now our application's network data pattern.
Well, you say it's not that important. I'm sorry. You're certainly right, but I'm still a little confused because I'm just wondering, like, if the server, like the servers, there's lots of servers in the world, right? And that server didn't know anything about this fuse thing that I made locally.
Yep.
It might not recognize it. Whereas if I got just the TLS channel, maybe local, it'd be like, oh yeah, I know how to talk to that.
Yeah, that's true.
So that's why I wondered about that. Yeah.
Yeah, that's, I think,
I mean, maybe you're the only one in the world using this right now, so you don't see the problem, but.
yeah, I haven't obviously run into that problem myself, but yeah, I think one way you could think about this is that, remember we had this like existential ops type.
Yeah.
So you can generate not only this, but like select of this and this.
Yeah, exactly. That's what I was wondering. Yeah. Okay, good. Thanks.
Isn't also that the sort of the assumption is that the fused version semantically behaves as
That's right. So I would think that it's like three GUIDs go along, right? The two old ones and the new one. So yeah. Anyway, sorry, go on.
Yep. Okay, so so far I've been explaining Bertha's features in the context of the traditional setting of like client-server communication. But modern applications can use not just like network features that we've been discussing so far, but also like multi-party connections. So to work with modern applications, Bertha ideally would support cases like multicast, where there's not just like a client and server, but like multiple senders and receivers. And in some cases, like a publish subscribe service, it's entirely asynchronous as well. So like the senders and receivers might not even be there at the same time. So how can we make negotiation work in this case? So the negotiation protocol actually extends this case fairly without that much modification. And our simple trick is that instead of relying on a live server to make decisions for us, we use a key value service. So when a client arrives, it picks the stack that it would like to use, and it tries to set that stack as the value for the connection's address in the key value store, and the connection's address is the key in the key value store. So if there's no other value set, then the client says, okay, I'm the only person in this connection, and that stack becomes the stack that the connection is going to use. If there is already a value set, then the service is going to return that stack. And what that means is that some other connection participants have already agreed on what the stack for this connection is going to be, and the client has to now make some decisions. So the first decision that the client could make is just to use this tunnel stack that the service has responded with and instantiate a connection and then like immediately begin participating in the connection. The second option is, again, just like last time, to return an error to the developer and say, okay, this is not compatible. Developer, please go fix this problem. And the third option is to do what we call an upgrade, where the client changes the stack via a two-phase commit, making sure that all of the other connection participants agree on the new stack that we're going to use before they all transition and start using it.
So is that kind of agreement always possible? Because if you have, there's like, I guess maybe local channel can also be a remote channel. So that's okay. I was thinking of a setting where some participants are local and some are remote, right? They would never agree on whether to use just the Unix pipe, right? Because some people can't use a Unix pipe.
So what would happen there is that you would use a remote thing, and then you would try to do a two-phase commit saying, okay, let's try to use the local one, and the other people wouldn't agree to the two-phase commit. It would fail,
so
and then
fall back to the remote that works for everybody.
Right. Exactly. Okay, so let's look at a case where upgrades can actually be useful. And with the publish subscribe connections that I was just talking about, it turns out that if the application wants messages to be ordered, it kind of matters for performance where that functionality is implemented. So the two choices are implementing it in the client or implementing or letting the service, the managed service, implement the ordering for us. So the difference between this is like having ordering implementation in our client or using like an SQS FIFO queue, which is which is what this like red bar is doing, and then this one is using the best effort queue. Okay, so this obviously has a latency cost. So the insight that we can make here is that if we just have one sender and one receiver, then using this best effort queue and doing the ordering ourselves can save us both time because we get better performance, and also money because we don't have to make more expensive FIFO API calls.
However, I'm reading the graph. So what is Bertha here? The colors are
there's-
AWS, Azure, and Kafka,
Yeah.
and then there's different setups.
There's no Bertha here. This is just
Ah,
an Bertha
okay,
here.
okay.
So actually, I mean, okay, there is Bertha here in that all of these things are built with Bertha,
Oh.
but like there's no like Bertha bar. that-
Oh, you're not comparing Bertha with anything else. You're
This is
saying
just
this is what
purely-
would happen.
This is saying like what would the performance be if I use client side versus server side measurement?
And that's a choice that Bertha makes available.
That's a choice that Bertha makes available.
Got it.
So this is great for if we have one sender and one receiver, but if we had multiple senders and multiple receivers, in order to do ordering, we would need to reach consensus among the clients for what the message ordering should be. And at that point, especially since I don't want to implement consensus in my clients because I'm a lazy person, I think it's just easier to let the service handle it. So ideally what we want to do is when there's one sender and one receiver, we use the client side implementation. And when there are multiple receivers or multiple senders, I can use the service side. So with Bertha, we can actually do this, unsurprisingly. So in this experiment here, at time t equals 0, we have one sender and one receiver. They very happily use client-side ordering until at time t equals 4 seconds, a second receiver shows up, and then we do this two-phase commit process and transition to the new channel stack, and then now we have those performance characteristics. So this is sort of a cool aspect of runtime reconfigurability. Like without something like Bertha and doing upgrades, you wouldn't be able to get this sort of dynamic transition, especially since like we're actually switching the queue that we're using. So here we're using the best effort queue, and then here we all agreed to switch to the FIFO queue instead. Okay, so I have 5 minutes
About a
left.
time, I know the AI goons are trying to get in here.
Right.
It's the
Okay,
story
yeah.
of computer
I can
science.
sort of speed up. I'm like almost done. Okay, so in this example application, we're doing sharding. I'm just going to skip this because I basically already talked about it before, and I'm going to talk about this instead. Here, what we're doing is, by the way, so this graph, just so like everyone understands. So on the x-axis, we have offered load to a key value service in thousands of operations per second, and on the y-axis, we have the request latency. And then this is like a box and whisker plot showing percentiles, so like P5, P25, P50, P75, P95. So ideally what we want is for things to be like very low and also go further to the right. That's better performance. So what we can see here is that we've applied an optimization to this channel stack in the orange case. And what the optimization does is instead of reading the message, deserializing it, figuring out where the key is, hashing that key, and then reserializing it to forward to the correct shard, we just read a fixed byte offset in the undeserialized message, like the raw bytes, and hash that instead and forward to the right right shard. And like normally this wouldn't be safe because
Time.
I'm out.
They're starting to yell at us, so.
Okay.
Can you, 30 seconds, go.
Yeah, normally this wouldn't be safe because you would have to, you don't know for sure that the fixed byte offset is the correct fixed byte offset. But because we have a tunnel stack, we can know that this byte offset is the correct thing because it's the specification is part of the tunnel stack.
Good.
All right.
Thank you.
Thank you, Akshay.
Talking outside, we just have to clear up the rooms these days.
Yeah, and thanks for everybody on Zoom for joining.